All right, let's continue with chapter 32, magnetism. So just as a brief introduction, magnetism has some elements that are like what we saw in electric charge, point charges. So magnetism has some of those similarities, but these are totally different things. You know, they are not exactly the same. While we had individual point charges, you know, when we looked at static electricity, we could have individual point charges like a positive charge and a negative charge. In magnetism, there are two poles, the north pole and the south pole. Both always come together. You can't separate the two, so there is no magnetic monopole. Okay, so that's one important difference. And so we'll talk a little bit about what we've learned about magnetic materials. So let's say that magnets come with two poles. The poles are a north pole and a south pole. We can say that, note that there is no magnetic monopole. If we split a magnet in two, we get two bar magnets, and each with two poles. And this is different from electric charges where we can have single charges. So let's look at a summary of some of the magnetic behaviors. So let's say this is a summary of magnetic properties. Or one, we can say that magnetic poles and electric charges. Number two, so magnetism is a long-range force, just like electricity. So just like you saw with the charged comb, paper clips will lead toward a bar magnet, just as paper will lead towards a charged comb. And I already mentioned that magnets have two poles. Two like poles repel and unlike poles attract. So isolated poles are magnetic monopoles. I've already mentioned that there are no magnetic monopoles. So unlike individual charges where you can have positive and negative individual charges, there are no isolated north pole or south pole for a magnet, so there are no individual poles. We identify a bar magnet, or we can say we identify the poles of a magnet by using a compass, and we can say that a pole that attracts a known north pole and repels a known south pole is a south pole. And then number 5, materials attracted to a magnet are called magnetic materials. So on Earth, we know that the Earth has a magnetic field, so we can look at the magnetism of the Earth. An example of a bar magnet, or let's say an example of a magnet is the Earth. We shall later identify it as a bar magnet, but an example of a magnet is the Earth. We can say the Earth behaves as if it has a large bar magnet. A north pole of a compass points to the geographic north of the Earth. This means the south magnetic pole is at the geographic north of the Earth. And then we can say that the geographic north is along the axis of rotation. And we can say it is offset from the magnetic south pole. Okay, so here is a picture of the Earth. Let's draw the Earth. And so we can say this is the geographic north. This is the axis of rotation of the Earth. So that's the geographic north. And you can think of the bar magnet as pointing along the Earth like that. So this is the north portion, and this is the south. So if we take a compass, the north needle of the compass points to the geographic north, which is the magnetic south. So this is the north of the needle, and this is the south. So this is the geographic north pole. And this angle between the two is called the declination, the magnetic declination. So basically, the magnetic pole moves around, and apparently it flips every few hundreds of thousands of years. Okay, let's go on next to the next section, which is the discovery of the magnetic field. People have known about magnetism for thousands of years. There is a stone called a lodestone which was used by navigators in ancient times because they noticed that it will align to the magnetic field or to a certain position on the Earth. And now we know that is the south magnetic pole. So if you take a lodestone, if it aligns to that north geographic pole, that is the south magnetic pole of the Earth. And so the lodestone can be used as a compass. So we've known about magnetism for thousands of years. But in the lab, the discovery of the magnetic field was by Ørsted, a gentleman by the name of Ørsted. He was basically studying the flow of currents through a wire. And by some chance, there was a compass close by, and whenever he had current flowing through the wire, the compass would flip. So that tells him that there is something going on around the wire which is causing the compass to flip. And that's how the magnetic field was discovered. And so the source of the magnetic field is a current flowing. One of the sources of the magnetic field is a current flowing through a wire. So we can conclude that magnetism is caused by an electric current in a wire. So let me just state again that magnetism has been known for thousands of years with the discovery of the magnetic field caused by Ørsted. We can say he discovered that the compass needle close to a wire will deflect when a current flowed through the wire. Ørsted discovered that magnetism is caused by electric current in a wire. We can determine the direction of the magnetic field around a current carrying wire by using the right-hand rule, RHR. So that means you wrap your fingers around a current carrying wire with your thumb pointing in the direction of current. That means then your fingers will curl in the direction in which the magnetic field points. So your fingers will curl around in the direction of the field lines. So you can imagine that you have a current carrying wire, current I going through the wire, and you wrap your fingers around it, which is the thumb, and your fingers go that way. Okay. That's not very good. That's not as good as I hoped it would be. But basically, your fingers wrap around like that. So this is the direction of the field when the thumb is pointing in the direction of the current. Okay, and it's just inverse to that. When the current is pointing downwards, then the field is reversed. Okay, so this is the direction of the current. So if you put a compass needle next to this field, then you see that the north portion points along the field that way. Okay, so you're going to have the north pole pointing like that. So the directions of the compass needle point in the direction of the field lines. Magnetic field is a vector quantity, so we shall look at the directions shortly. So we use the symbol B, and we shall say it is a vector. So based on that, we can come up with a convention. So we shall use B, a convention for the magnetic field B and a current carrying wire I. And we shall say that if the wire is pointing out of the page, we shall use a dot. Okay, let me put a dot here instead. So if the wire points out of the page, we shall use a dot. If the wire points into the page, we shall use a cross. And then we shall say field lines B, magnetic field out of page, we shall use dots like that. And for magnetic field into the page, we shall use crosses. Okay, so we've talked a little bit about the field already. I'll talk about it here. So if you recall, we used the electric field as a way to introduce the action at a distance that the field exerts on charged particles. So in the same way, the long-range effect of magnetism can be explained by a magnetic field. The field is basically a distortion of the space around the current carrying wire. A magnetic field is created at all points around the current carrying wire. Magnetic field is a vector. I'll just write B field. It's a vector, and the field exerts a force on magnetic poles. So if you put a compass in a magnetic field where the field lines are pointing that way, it's going to have forces on it that will attempt to line it up with the field. So this is the magnetic field B, And so there will be a force this way, F, and another force that way, F. The forces will tend to line or rotate the compass so that it lines up with the field. Okay, so the forces will rotate the compass so it lines up with the field. So let's look at the current carrying wire. So we have a current carrying wire pointing into the page, and we can see that, so in this case, we have this wire into the page. So since it's into the page, then by right-hand rule, the field lines are going to be like that, all the way around it. And so we have field lines going this way. And if you imagine drawing vectors in the position of these fields, so at each point here, there's going to be the magnetic vector, or the magnetic field is going to point like that. Same way, you're going to have vectors pointing this way. And I'm drawing the vectors shorter and shorter because the field lines should be getting smaller and weaker as you get farther away. So that's why I've drawn them that way, where they are shorter. The magnetic field B should be tangent to the field lines, as you can see there. So that's what I've tried to draw for you. So we can say that B vectors are tangent to the field lines. So we've already established that the magnetic field is due to the current in a current carrying wire. So let's look at the next section, 32.3, the source of the magnetic field. So we can say that Ørsted discovered that magnetism was due to current in an electric current, or was caused by an electric current. Let's use the word caused by an electric current. And then we can say that we know that current is produced by the movement of charge or movement of charges. So based upon that, we can say that the moving charges, it is the source of the magnetic field. Okay, moving charges are the source, and so we can we will write a formula for that. So just like we saw with electric charges, the electric field can be described for a point charge by using Coulomb's law. So for a magnetic point charge, or for a point charge moving, we can say the magnetic field of a point charge can be written also, and is given by something called the Biot-Savart law. So we can say the magnetic field of a point charge is equal to mu naught over 4 pi, and then we shall have Q, which is a charge, V cross R hat divided by R squared. So for example, if you have a point charge moving at some point in space with a velocity V, and you want to find the magnetic field at some point here, the magnetic field is going to be pointing that way by the right-hand rule. So the distance from the point charge to the field is the distance R, where unit normal vector is R hat pointing this way, and this is R. The angle between the two is theta, that way. Okay, and so based upon that, we will see that the magnetic field points in the direction perpendicular to the plane of R and V. So I'll just write V and R. So this is a cross product. This means the direction of V is due to the cross product between V and R. Okay, so that's a cross product V cross R. I'll define the terms shortly. So we can say that the magnetic field of the point charge is equal to mu naught over 4 pi, and then we have the charge Q. This is the charge Q. So I'll just put Q here, and then QV cross R hat over R squared. So this is the letter mu. So this is mu naught. Mu naught just means that naught is the 0 at the bottom. So the letter mu naught, if you spell naught that way, is the permeability of free space. V, which is velocity, is the velocity of the charge. We know, of course, that Q is charge, and R hat is a unit normal vector in the direction of R. So we can write the magnetic field of the point charge to be equal to mu naught over 4 pi, and then we have Q B sine theta divided by R squared. Well, I'm just taking the cross product, and since I took the cross product, Then r hat is a unit normal vector. I just have v sine theta, and I'm dividing by r squared, which is the distance from the charge to the point where b is being evaluated or being found. So this equation is a Biot-Savart law for a charge. So that's the law for a point charge, and we've already said the magnetic field is a vector. The unit is Tesla. The letter for that to be T. 1 Tesla is 1 Newton per ampere meter, and mu naught, the permeability of free space, is given by 4 pi times 10 to negative 7 Tesla meters per ampere. Okay. Or it's also written as 1.257 times 10 to negative 6 Tesla meters ampere. So assuming that you multiply by 4 pi, that's what you get. The field, the magnetic field of the Earth is 5 times 10 to negative 5 Tesla, or 0.5 microtesla. So the magnetic field at the surface of the Earth is very small. If you have a superconducting magnet, it's about 10 Tesla. Okay, so if you look at the magnets in the hospital, those magnets that they use for MRI, those are 1.5 Tesla. They are very strong fields compared to the Earth's magnet. If you have those permanent magnets they use for lifting up cars in the junkyard, those will be about 3 Tesla. So the magnetic forces are very strong. All right, so let's go on. So since the magnetic field is a vector, we can add different B's for different magnetic fields by using the principle of superposition. And so suppose we have B, NB, so we can say B total is equal to B1 plus B2 plus Bn. Okay, so this is just a principle of superposition for magnetic fields. So for example, what is the net magnetic field at a given point due to B1 and B2? Okay, so let's say we have a wire like that. So we have a wire where there's a magnetic field going this way. Let's call this B1 equals 2.5 Tesla. And then we have another field going that way. So we want to find B total. So B total is just going to be equal to B1 plus negative of B2, of course, because these are all vectors. So this will be 2.5 Tesla minus 1.5 Tesla, which is equal to 1 Tesla. So the net magnetic field from those two field vectors is just 1 Tesla. Okay, so we can say example or exercise. So let's find the net magnetic field for the arrangement below. So let's say that we have, so let's say A, the field lines are B1 and B2. So do that exercise and tell me what you get. So what is A? Okay, so we have B1. Well, you can, let's use a convention that up is positive and down is negative.
Negative 1.5.
Yeah, so,
1.5.
Right, so we can have B2 minus B1, which is equal to 1.5 Tesla minus 3 Tesla. So this will be equal to negative 1.5 Tesla. So think of magnetic fields just the same way as we think of vectors. Okay. And then for part B, what do you have for the net field? 2.5. So like I said, this is a vector quantity. So how are you going to add this? It's basically Pythagoras theorem.
Square root 6.25.
Yeah, so you're going to do square root of 2 squared plus 1.5 squared, which is the square root of 6.25, which is equal to what? 2.5. Very good. So that's your net field. What about the direction? Remember, it's a vector quantity. So let's say the direction phi is equal to tangent inverse of, and you can take the one pointing down to be the y. So around 1.5 divided by 2. What does that give us?
36.5 degrees.
Okay, so let's say about 37 degrees. So the net is going to be, if you like, we can redraw it. So for this one, this is 2, this is B2, I guess, and this is B1. That's right. Okay, so what we have is a net this way, and this angle is phi. Okay, so this is your net magnetic field, BT. So let's stop here so that when we come back on Thursday, we shall start off fresh with the magnetic field of a current